Okay, real gases versus ideal gases. So obviously, real gases, because they're real and they're not ideal, don't always behave as we assume they will according to those assumptions about ideal behavior. The two faultiest assumptions that you're expected to know about first is that gas particles experience no attraction for other gas particles. So normally gas particles are so far apart and they do have such relatively weak attractions anyways for other particles that this can essentially be considered to be true, so under normal conditions. But when will this assumption not hold true? Well, mainly this assumption will not hold true if we can get gas particles really close together, or if we can slow them down, or some combination of both. So how do we get gas particles really close together? Well, that's basically describing high pressure. So if you put a gas under pressure, the gas particles get closer together, and the very weak attractions that they have for each other actually can now take effect. So normally they're too far apart to take effect, but if you get the gas particles close enough together under high enough pressure, you start to see the effect of the attractions between the particles. And so what that effect is that the volume of a real gas will actually be smaller than that predicted by the ideal gas assumptions. So real gases under relatively high pressures, somewhat high pressures, tend to be smaller than what we would otherwise predict, because the high pressure brings them close enough together so that they can have attractions having an effect. Now, the other way that we can do this, I said, is if we slow them down. So slow down the particles if they move more slowly. How do we slow down particles? Well, we lower their temperature. If we slow down particles enough, then that also might give the particles a chance to where their attractions could actually have an impact. So we already would predict that a gas shrinks when you put it under lower temperature, but a real gas might shrink actually even more than you would predict based on the ideal gas law. So when these attractions actually have an impact and this assumption no longer holds true, then we see that real gases are smaller than ideal gases. Okay, the other assumption that is faultiest is that the gas particles themselves have negligible volume, so they basically don't have any volume. Well, under normal conditions, gas particles are so far apart that, yeah, this basically is the way it acts. It's the way it seems, so we can ignore their volume. Well, when will this not hold true? When would we expect a real gas's, the volume of its particles to actually matter? Well, if you go past what I called up here, high pressure, and you go to extremely high pressure, so a little bit of pressure pushes the gas particles closer together, and their attractions start to take effect, and the gas might sort of shrink compared to what you expect. But according to ideal gases, we can compress them forever. Since they don't take up any space, the particles, under our assumptions, that means they are infinitely compressible, that we should be able to keep shoving them down into smaller and smaller spaces. Well, obviously, at a certain point, there are actual particles there. So if you get to a high enough pressure, then the gas particle volume starts to push back. So it's no longer negligible. And so in this instance, at the very high pressures, we see that the volume of real gases is bigger than that predicted by the ideal gas law. Because the ideal gas law, or these assumptions about ideal gases, tells us that we can compress forever, but real gases obviously can't be compressed forever. At some point, they will push back. So you're expected to know under which conditions the gases tend to deviate from ideal behavior, and in what direction. How do they deviate from ideal behavior? Usually the focus is on the volume, so whether or not the volume of a real gas will be smaller or larger than predicted based on the assumptions about ideal gases.